In the construction of mega bridges for China's high-speed railway, a specialized multi-wheeled vehicle plays a crucial role. These vehicles are used to transport massive bridge sections to the construction site. Once the sections are delivered, they are carefully aligned with precision. The sections are then lifted and connected to the pre-positioned parts of the bridge structure. This method ensures that each segment is moved and positioned efficiently, reducing the time required for installation. This transportation technique is key to building such large-scale infrastructure in a safe and controlled manner. The use of multi-wheeled vehicles also minimizes the risk of damage to the structure during transport, which is vital given the immense size and weight of the bridge sections. These vehicles are equipped with advanced hydraulic systems to handle the heavy loads with ease and maintain the stability of the sections during movement. After the segments are aligned and secured, the assembly continues as workers and engineers ensure each piece is perfectly positioned. The result is a high-speed railway bridge that provides a smooth, safe, and stable route for the trains that will cross it. From barren soil to a finished road, this is where precision meets productivity. At the heart of this transformation lies a 240-ton-per-hour Sigma asphalt plant, an industrial workhorse engineered for continuous, high-capacity performance in road construction. It's not just about building roads, it's about building durability that withstands time and traffic. Every stage of production is calibrated for accuracy and consistency. The process begins with aggregates of various sizes, stored in separate hoppers. Each material is conveyed to a drying drum, where it's heated, and moisture is eliminated. Next, the hot aggregates are lifted to the screening unit, where they are separated by size and stored in hot bins. Once sorted, the materials are fed into the mixing unit, where asphalt binder is injected. This forms a hot mix that meets strict specifications. The plant operates with advanced controls that regulate temperature, blending ratio, and throughput, ensuring consistent quality. The prepared asphalt mix is transferred to dump trucks, which transport it directly to the paving site. On location, a large tracked paver spreads the material evenly. Its screed ensures a uniform thickness and compaction level as the machine progresses along the route. A second paver works in tandem for wider lanes, while workers oversee the edges and alignment. The screed's heated bottom and vibration system contribute to a smooth, dense surface. Behind the pavers, a pneumatic roller and tandem roller follow up to achieve final compaction. These machines ensure that the asphalt layer reaches optimal density and durability. This streamlined operation, from plant to pavement, relies on tight coordination between machines and personnel. With its 240 TPH capacity, the Sigma plant supports large-scale roadwork with minimal downtime. Whether laying a new highway or reinforcing old infrastructure, the system delivers efficiency without compromise. What begins as raw stone and bitumen ends as the path we drive on, built one precise layer at a time. When infrastructure demands precision under pressure, heavy lift operations step in. On Road 20 in Lenomme, massive concrete beams, some weighing up to 200 tons, are installed with hydraulic cranes ranging from 250 to 500 tons in capacity. Each beam is delivered by specialized transporters, positioned with pinpoint accuracy beneath the cranes. Operators coordinate every move via radio, adjusting lift angles and synchronization in real time. In one phase, twin 250-ton cranes work in tandem to hoist 80-ton beams, maneuvering slowly into place over pre-poured piers. In another, a 500-ton crane lifts 200-ton girders requiring extensive counterweights and precise boom extension. Safety protocols guide every moment, from securing the slings to final placement. Even wind speed is monitored to avoid instability during lifts. This isn't just construction, it's engineered choreography. Every load, every rotation, every centimeter matters when building the backbone of a highway. When a 349 excavator sinks into soft terrain, recovery begins with reshaping the ground. A bulldozer moves in first, leveling and compacting the surrounding soil to form a stable ramp. Instead of pulling it out, crews let the excavator climb out on its own, using controlled movements and firm traction. No brute force, just thoughtful groundwork. Slowly but steadily, the machine regains grip and crawls free, back on solid earth, ready for the next task. The CAT 994K wheel loader revolutionizes material handling with a 150% improvement in efficiency while reducing carbon emissions. Custom built for ROM coal operations, this powerful machine is equipped with a massive 40 cubic meter bucket, allowing faster and more efficient loading. Compared to the previous model, the 994K can load a 789C truck in just 4 buckets, cutting down on operational time significantly. During operation, the loader runs up to 10 hours per shift, maintaining consistent output with fewer refueling stops. Batch Fire Resources, focused on reducing its environmental footprint, benefits from the 994K's advanced emissions technology. The machine's engine provides cleaner exhaust emissions, meeting stringent sustainability goals. With improved comfort features and lower noise levels, operators enjoy enhanced ergonomics and performance. The production process of the concrete pump truck is an intricate combination of steel, hydraulics, and concrete machinery, transforming them into a specialized piece of equipment ready for demanding work sites. The process begins by adjusting an existing machine model to meet local standards. Mechanical and electronic systems are calibrated, and the control software is fine-tuned for precision. Technicians perform functional checks on key components, such as the boom joints, pump module, and pressure regulation system. The assembly process occurs in stages. The main frame is mounted onto the truck chassis. Supports, hydraulic connections, and reinforcing structures are added to ensure load-bearing capacity and the proper operation of the pump boom. Hydraulic cylinders are installed and connected to the central control system. Here, the operational range of the boom joints is tested to ensure they extend and retract correctly. The concrete hopper system is securely fixed to the rear platform of the truck. The hopper cover, agitator blades, and pressure connections are tightly installed. The concrete discharge line is connected to double-layer pipes running along the boom's length. This ensures a seamless flow of concrete during pumping and helps maintain consistent pressure. Next, the electrical system is installed. Control boxes, sensors, and backup modules are mounted and linked to the central interface. This includes safety sensors such as boom position sensors, emergency stop switches, and flow limiters. The system also features automated diagnostic capabilities, allowing real-time performance monitoring and troubleshooting. In the intermediate stage, high-stress joints are reinforced using automatic welding machines. Components such as stabilizing legs and stability equipment are installed and tested hydraulically. These parts ensure the machine operates safely on uneven terrain. Hydraulic pressure is adjusted and verified to meet specific operating standards before the machine progresses to the next stage. The pump boom is assembled gradually, with each segment aligned and fixed with pins and hydraulic connections. The system includes fault sensors to detect if the boom hasn't fully retracted, minimizing risks during work on the construction site. Additionally, hydraulic hoses are carefully routed to prevent kinks or damage during operation. At the same time, the steel components are sandblasted and coated. A dedicated paint room is used to apply corrosion-resistant coatings and finalize the color finish. This coating not only enhances the machine's aesthetic appeal, but also improves its longevity, protecting it against harsh environmental conditions. Once assembly is complete, the pump system undergoes load testing. Simulated concrete pressure is pumped through the entire system to check for leaks, flow rates, and pressure losses. Every joint, from the hopper to the end of the hose, must be fully sealed. The pump's performance is analyzed at varying pressure levels to ensure it meets operational specifications. The final stage takes place at the construction site. In the video, workers demonstrate how to guide the boom during concrete pouring. The controls are operated remotely, allowing precise positioning without approaching the end of the hose. The system is stabilized using hydraulic legs, and the flow rate is adjusted according to the job requirements. Real-time monitoring ensures that the concrete is pumped at the optimal rate for the specific project needs. The entire process is closely monitored for pressure, boom oscillation, and engine performance. Data is recorded at each test cycle. This data is analyzed to assess the system's overall efficiency, allowing for any adjustments to be made before final deployment. Before shipment, the vehicle undergoes an outdoor field test. The operator drives the truck to test acceleration, braking, and the boom's response under real-world vibrations during pumping. This ensures the structural durability when operating in the field. Additionally, the field test includes assessing the truck's stability and load-bearing capacity under varied conditions. By integrating mechanical assembly, electronic calibration, and concrete pump simulation, this process results in a fully assembled machine, ready to perform in the challenging conditions of a construction site. The end product is a highly reliable and efficient concrete pump truck that meets the rigorous demands of the construction industry. Stretching across the mighty Ganga River, the Mahatma Gandhi Setup is not just a bridge, it's a critical artery linking North and South Bihar. With rising traffic and structural fatigue, the Indian Ministry of Road Transport and Highways initiated a groundbreaking rehabilitation. Awarded to Afghans and Sibmost under EPC mode, the project aimed to completely replace the bridge's aging RCC superstructure with high-performance steel trusses. The western flank spans 5.6 kilometers, with 46 spans in total, 26 over land, 10 across a seasonal flow region, and 10 over water. To ease traffic, a pontoon bridge and diversion systems were constructed, ensuring minimal disruption. Dismantling 75,000 cubic meters of reinforced concrete demanded precise execution. Over land, a high-reach boom jaw cutter was deployed, integrated with anti-dust systems. Over water, wire saw cutters carefully sliced through sections, which were then lifted by gantry cranes and placed onto barges for transport. All debris was recycled or safely discarded. No rubble was allowed to contaminate the Ganga. Each steel truss segment was prefabricated off-site, transported in sections, and assembled with millimeter-level alignment to ensure structural integrity across spans. Monsoon conditions required dynamic planning, and engineers adapted operations on the fly. New pier caps were built to support 720-ton steel truss segments, each designed for a 100-year lifespan. On land, ground support systems enabled assembly, while cantilever erection techniques were used over water. Altogether, 66,360 metric tons of steel are being used in the transformation. Through adaptive engineering and environmental mindfulness, this bridge is not just being rebuilt, it's being future-proofed, turning one of India's oldest major bridges into a modern marvel set to serve generations to come. The third Bosphorus Bridge, also known as the Yavuz Sultan Selim Bridge, stands as a monumental achievement in modern civil engineering. As part of the broader North Marmara Highway project, this iconic structure stretches across the Bosphorus Strait in Istanbul, Turkey, uniting the continents of Europe and Asia with a single powerful sweep of steel and concrete. The bridge represents not just a transportation link, but also a testament to cutting-edge construction methods, high-performance materials, and visionary design. Construction on this massive infrastructure endeavor began with thousands of workers, engineers, and project managers collaborating on a mission that blended technical complexity with architectural elegance. The project was developed under a build-operate-transfer model, incorporating the combined efforts of Turkish and international contractors. The objective was clear: to construct a multifunctional bridge that would significantly reduce traffic congestion in Istanbul while simultaneously supporting railway and highway transport on a unified platform. An ambition never before attempted at such a scale. At the heart of this bridge's innovation is its dual-purpose design. It is the first suspension bridge in the world that carries both 8 lanes of motorway and 2 railway tracks on the same deck. The integration of these systems posed a significant challenge for designers and engineers, requiring highly specialized load distribution calculations and aerodynamic simulations to ensure structural stability. To ensure aerodynamic performance, the deck's profile was engineered to minimize vortex shedding, reducing oscillations under high wind conditions. Wind tunnel testing and computer-aided modeling were extensively used to account for Istanbul's seismic activity and varying weather conditions, ensuring that the bridge could withstand high winds, earthquakes, and intense traffic loads. The bridge also integrates cutting-edge technology to ensure longevity and operational efficiency. Advanced monitoring systems have been installed to track structural health, providing real-time data on vibrations, temperature, and stress, enabling predictive maintenance. Furthermore, The bridge's construction was supported by environmentally sustainable practices, including the use of biodegradable materials during temporary structures and measures to minimize the ecological impact on the surrounding marine life. To meet international standards, engineers also consulted with seismic experts to implement base isolation techniques and dynamic dampers, increasing the bridge's resilience against potential earthquake-induced oscillations. The integration of these components helps dissipate energy during seismic events, safeguarding the structure and its users. Towering over the Bosphorus at a height of 322 meters, the bridge's pylons are among the tallest in the world for a suspension structure. Each tower required thorough planning and the installation of massive steel components. More than 13,000 tons of high-tensile cables were used to suspend the bridge deck, and 176 individual cable strands, more than previously reported, were anchored with precision to distribute the massive weight evenly. These cables span a main distance of 1,408 meters, making it the longest suspension bridge in the world that carries a railway system. The bridge deck itself is composed of 59 prefabricated steel panels, each weighing up to 940 tons. These panels were manufactured off-site under strict quality control standards, and then transported to the installation site via special barges. Giant floating cranes capable of lifting over 1,000 tons were employed to hoist and align the sections mid-air, requiring advanced GPS positioning systems and laser-guided measurements to ensure millimeter-level accuracy. Innovative robotic welding systems were used during steel fabrication, enhancing joint strength and reducing human error in critical load-bearing sections. The assembly was a synchronized operation, coordinated with the construction progress of the towers to maintain balance and prevent structural distortion. To address long-term durability, all structural steel was coated with multi-layer protective systems to withstand corrosion from the salty sea air. Each component underwent accelerated life testing in laboratories to simulate decades of exposure. Throughout the construction process, time management and safety protocols were paramount. Work proceeded in 3 shifts, 24 hours a day, to meet demanding deadlines without compromising on safety. More than 6,500 workers were involved at peak construction, supported by over 500 engineers and supervisors. The use of modular construction techniques allowed for greater efficiency and reduced on-site labor complexity, enabling a faster, more precise assembly of components. Dedicated training programs were implemented for construction staff to ensure familiarity with the specialized machinery and complex assembly techniques used in such a pioneering project. These efforts led to a recordable incident rate well below industry averages. Emergency response planning was also embedded into the bridge's operation strategy. The structure includes multiple emergency lanes, dedicated pedestrian inspection routes, and surveillance systems that monitor traffic and weather conditions at all times. Rescue access points were integrated at intervals along the bridge, allowing emergency personnel to reach any location within minutes during critical incidents. Beyond its structural and functional capabilities, the third Bosphorus Bridge is a symbol of architectural finesse. Its sleek profile and elegant cable arrangement were carefully designed to blend harmoniously with the surrounding landscape. The pylons were inspired by the architecture of Ottoman-era structures, bringing historical significance into a contemporary context. At night, the bridge is illuminated by an intelligent lighting system that shifts in color and intensity, creating a dynamic visual landmark visible from across the city. To accommodate tourism and cultural engagement, a nearby observation deck was constructed, allowing visitors to learn about the bridge's design through interactive exhibits and panoramic views. Environmental sustainability was also a key consideration. During construction, strict environmental impact assessments were carried out to minimize disruption to the Bosphorus ecosystem. The bridge's design allows for minimal interference with maritime traffic, maintaining clear passage for ships underneath its expansive central span. Moreover, the project included noise reduction barriers, advanced drainage systems, and measures to prevent soil erosion and water contamination during construction. Biodegradable materials were used for temporary structures, and a reforestation initiative was launched to offset ecological disruption along the construction corridor. Once fully operational, the third Bosphorus Bridge is expected to divert a significant portion of the vehicle traffic from Istanbul's inner city. Estimates suggest it will handle over 135,000 vehicles daily, alleviating pressure on the existing Bosphorus and Fatih Sultan Mehmet bridges. The inclusion of rail lines not only facilitates commuter traffic but also enhances cargo movement, linking key logistics centers and ports between the continents. This makes the bridge a crucial asset for international trade, turning Istanbul into a more prominent global transport hub. Additional logistics hubs are being developed near the bridge to fully capitalize on its freight handling potential, aiming to create seamless intermodal transfer points between road and rail. The bridge has also set new benchmarks for public-private collaboration and infrastructure development, drawing interest from international policymakers and investors. Spanning a total length of 2,164 meters with a width of 59 meters, the widest suspension bridge in the world, the structure embodies both strength and versatility. It serves as a living example of how infrastructure can integrate advanced engineering, sustainability, functionality, and beauty. The bridge's completion marks a pivotal moment in Turkey's modernization efforts, reflecting the country's capability to execute world-class projects. The bridge also offers significant strategic advantages. It serves as an essential bypass route for heavy vehicles that were previously forced to enter city traffic, contributing to noise and air pollution. With this new route, Istanbul's urban environment is expected to experience considerable improvement. The high-speed rail system integrated into the bridge is also designed to accommodate future railway expansion plans, including potential connections to cross-border transport corridors. This future-proofing ensures that the bridge will continue to serve growing transportation demands in the decades to come. Educational institutions across Turkey have incorporated the project into civil engineering curricula, using it as a real-world case study for next-generation engineers. Advanced monitoring systems have been installed throughout the structure to ensure continuous health checks of the bridge. These sensors provide real-time data on stress, vibration, and temperature, allowing for predictive maintenance and immediate response to any anomalies. In addition, machine learning algorithms analyze sensor data to detect early signs of wear or abnormal patterns, enabling intervention before issues escalate. The bridge's maintenance operations are supported by an advanced control center, equipped with state-of-the-art diagnostic tools and automated maintenance scheduling. This allows operators to monitor the entire structure and anticipate service needs before issues arise. Notably, the economic benefits of the bridge are projected to be significant. Reduced fuel consumption, shorter travel times, and more efficient logistics are expected to boost Turkey's economy by billions of dollars annually through increased trade and productivity. The project also created thousands of jobs throughout its development, from design to construction and now to operations and logistics. This has had a considerable impact on the local economy and provided new opportunities for skilled labor. The bridge's opening ceremony was attended by global leaders, symbolizing Turkey's rising position as a central player in Eurasian transport networks. Its design and construction have already been featured in several international engineering journals and documentaries. As global demand rises for resilient infrastructure in seismically active regions, the third Bosphorus Bridge is frequently cited in international forums as a model of integrated safety and design excellence. Looking forward, the Yavuz Sultan Selim Bridge is expected to inspire a new generation of infrastructure projects worldwide. Its successful execution provides a replicable model for integrating multimodal transport systems into a single structure. The bridge has also become a point of civic pride. Tourists and locals alike flock to its viewpoints to witness the scale and elegance of the structure, contributing to Istanbul's growing reputation as a destination for architectural tourism. As the final stages of testing and commissioning are carried out, the third Bosphorus Bridge stands ready to open a new chapter in transcontinental connectivity. It is more than a bridge, it is a bold statement of ambition, a marvel of human ingenuity, and a symbol of a nation striding confidently into the future.